Good evening. Good evening, students. Good evening, professor. This is Dennis Karumba. Today I was doing a sequence detector design. What's my objective? I had to write I had to write a whole report on this one, but because the other one I could not get the right words to say, so that's why I had to write it down on this one. So my objective, the main objective of the lab is to design and build and test sequence circuit which detects the sequence 0010 from any input stream. My introduction is the understanding of the sequence logic circuit and finite machines is essential in the logic design to control digital systems. This lab presents the design and implementation of Mary machine sequence detector to detect my sequence, which was 0010 with overlapping sequence. This report documents the design processes, circuit schematic stimulation of the output in multisim, which I'm going to show you later about my multisim, using the logic analyzer testing and implementation. The results and the challenges from the design and stimulation testing and implementation. Down here is a general form of the Mali state, which I used, general form of Mali machines, and a block design of the sequence, as you can see over here. The steps I followed to set up my sequence detector was as when designing the sequence circuit, the following procedures is followed. Formulation of a state table, which I'm going to show you here. A state is a unique configuration of information in a machine. States designs are used to instruct the form and function of the state. The initial states is the reset state. The states are added as each successive input is recognized. The final state represents the input sequence occurrence. State transition arc specify an occurrence when a symbol is proper or not in proper sequence detected. Then after formulating the state, I went to how the assignment. Then the state is obtained from the state diagram. It is then checked if it is reduced in the number of the state. Then I did my K-map for the flop input. Output is Z. The circuit can be represented. The method I used, I went to the implementation I used for my state diagram. For any given state, there is a finite number of the next possible state. Depending on the inputs, the next possible state becomes the new present state. My state A, as people may call it, my S0, my state 0, I had 4 of them, which is my state A, state B, state C, and state D. So my state A is the state we arrived at for any time. This is my state table, as you can see over here. This is my state. So I'm going to tell you how I formulated it. My state A is the state we arrived at for any time we receive an input X as 1. It goes back to, if you have an input, it goes back to state A. That's what it's trying to say over here. X from the initial. The first time we received an input as X to be 0. If you have an input to be X as 0, the transition state moves. If you have an input as 0, it's going to go to transitions to be with 0 output, which goes here with 0. If otherwise, an input of X remains at A. If you have the input as 1, it remains at the state A. If we receive an input as X at our state B, for the second time, the transition moves from B. If we have an input as 0, it goes to state C with 0 input. If the second input is X, the transition states B. From here, if you have an input of 1, it's going to go back to state A. That's why it says here in my writing with 0 output and starts all over again. Then if you have, it's going to start all over again. Let's go back here. When we receive the third input as X equals to 1, as from here, we transition from state C to D. If you have 1, it goes to D. With 0 output, if the input is X is 0, it will stay. If you have our input as 0, it's gonna stay at state C, stays as output. Finally, when the input is X 0, the sequence is 0. When you hear it recognizes our sequence, then input as X is equal to 0. Then the subsequence of the site of the sequence is 0, 0. Thus, we move from state D to B here with 1 as output, as you can see over there. From there, then as you can see, there are 4 states. 1 in my output, as you can see, my present, my next. This is the implementation of this. As you can see, from A to B, we have 0 with our input as 0. From B to C, we have our output from 0 to 0 as our output. From C to C, we had 0, 0. And from D to B, we had our output as 1 and 0. From there, then that's our A was represented by 0, 0, B was represented by 0, 1, C was represented by 1, 0, and D was 1, 1. As we go here, then I went to my K-map. As you can see how I did my K-map, our input, I go 1, 1. For us to deliver the equation, the K-map for the flip-flop D1 and D2 for output can now be obtained as follows. This is how I obtain my D1, D2, and our output Z to deliver my equation for us to draw the schematic. As you can see, D1, Y1 here, what we got here, plus Y. That's how I delivered my equation. This is my first drawing of my schematic. As you can see, my input here, I have my 1 input and 1 output over here. As you can see, as I show you on my breadboard here, we had 3 input AND gate. As you can see, we had a 3 input, but we were not given. So I tried using two input AND gate, but then I ran out of them because we were not given much of it. As you can see, I tried as much as I could. As you can see here, it's on. As you can see, it's on, but I could not run out. My input was 0. I tried, but as I'm gonna show you my results on my schematic, here was not able to work since I was running out of stuff. I tried as much as I could to connect it. It was too many, but I ran out of my my AND gates. But I tried my best. As you can see, if we had the 3 input, which I did on my. This is my schematic, which is a printout. I'm gonna show here on my laptop. This is my schematic. This is my schematic. As you can see, if as you can see right now, it's on. When the switch is on, when the switch here, as you can see, my switch is, when the switch is on, my output light becomes 1, which is our output becomes 1, which makes it light. As you can see, when the circuit is off, when it's closed off, the lights, as you can see here, it went off. Let me show you again. As you can see, it's on. Then, as you can see, then it went. As you can see, it's off. Then it's on. That's how when it's on when we put it, our output, because when it's on, when the switch is on, the light, our output is 1, which makes it light on. And then I'm gonna show you my logic analyzer here. Hold up. Yeah, that was stop. Oh, I need to make it run. Yeah, as you can see, that's my logic. As you can see, it's running. That was my logic analyzer. Okay. So to what I concluded to, let me show you because I could not print the other one, my Word document here. Oh, here. To what was my the knowledge? My conclusion was the knowledge on the design of the sequence detector is helpful in implementation digital system. The Melee finite state machine has widely been used in application of the sequence circuit to detector sequence. It can be concluded that whichever the sequence to be detected, with proper design process and testing, this can be achieved. I had some difficulty in just a few things, but if we had the 3 input AND gate, I could have done it, but I ran out. If I could have had some more, I could have run it, but I could not be able to finish or show any light on. But probably next time I could, if we had time. But the knowledge I acquire is thanks to Dr. Oasis. I thank you for everything, and thanks for the students who we were able to communicate in class. And all I can say is have a good Merry Christmas and a Happy New Year. See you on the next semester. Thank you and have a wonderful year.